Welcome everybody. Myself Dr. Himani, and today we are going to start with energy metabolism and nutrition. What is nutrition? Nutrition is the science of intake, absorption, metabolism and utilization of food substances by the body for growth, maintenance, reproduction and repair of the tissues. It encompasses the physiological and biochemical processes involved in transforming dietary substances into energy and body constituents. Calorific value. Calorific value refers to the energy yield from food substances upon complete oxidation. Energy content is measured in calories or kilocalories. Since calorie is a very small unit, we use kilocalories for regular purposes. So 1 calorie is basically a heat required to raise the temperature of 1 gram of water by 1 degree Celsius. 1 kilocalories equates to 1000 calories, which is equal to 4.2 kilojoules. Standard method of determination of calories, calorific value, is bomb calorimeter. Here, like this is the equipment, and food is combusted in the presence of oxygen. Now, calorific value of macronutrients. So, in the case of carbohydrates, the calorific value of carbohydrates is 4 kilocalorie per gram, and in fats it is 9 kilocalorie per gram, and proteins provide 4.2 kilocalorie per gram, and alcohol gives 7 kilocalories per gram. But thing to remember is that the alcohol, it does provide kilocalories, like 7 kilocalories, which seems to be higher than carbohydrates and proteins, but the calories that alcohol provides, they are empty. Empty in the sense that they do not provide any nutrition, any nutrients, and they are not used for the bodily growth functions and immune repair and other functions, regeneration purpose. Respiratory quotient. Respiratory quotient is defined as the volume of CO2 produced to the volume of oxygen consumed, measured per gram of substrate oxidized. So, you can say respiratory quotient equals to volume of CO2 produced in liters per gram upon volume of oxygen consumed in liters per gram. It reflects the metabolic substrate being utilized for the energy production. So, respiratory quotient for macronutrients. So, the carbohydrates, the macronutrient is, the respiratory quotient is 1.0. In fats, it is 0.71. Proteins, the respiratory quotient is 0.81. And in the mixed diet, it is 0.82 to 0.85. Carbohydrate metabolism. Since we have seen that the respiratory quotient of carbohydrate metabolism, it equates to 1, that means equal CO2 output and oxygen input. That means the amount of CO2 that is produced is equal to the amount of oxygen that is consumed. In fat metabolism, the respiratory quotient is 0.7. That means greater oxygen requirement. That means more oxygen is utilized than the CO2 produced. And then in protein metabolism, the respiratory quotient is approximately equivalent to 0.8, which is intermediate value due to partial oxidation and nitrogen excretion. In mixed diet, respiratory quotient typically is between 0.82 to 0.85. So, respiratory quotient decreases when fat metabolism predominates. This is seen in diabetes mellitus, fasting and ketogenic states, right? Why so? Because in diabetes mellitus, there is insulin deficiency. So, there is a condition of intracellular hypoglycemia. So, the cells, they predominantly depend upon fats for the fuel, right? In fasting also, there is lack of carbohydrates. So, predominantly fat is being used. Lowest respiratory quotient is observed during active ketolysis. So, this is helpful in indirect calorimetry for calculating energy expenditure and metabolic status in ICU settings. Energy yield per liter of oxygen consumed. Despite differences in respiratory quotient, energy yield per liter of oxygen consumed is approximately constant, that is is 20 kilojoules per liter of oxygen. That is for all macronutrients. Energy requirement of a normal person. So while calculating the energy requirement, we have to consider the energy required for, firstly, maintenance of basal metabolic rate. Second is specific dynamic action or thermogenic effect of food. And then extra energy expenditure for physical activities. So these are the things that need to be considered for calculating the energy requirement of a normal person. What is basal metabolic rate? Basal metabolic rate is the minimum amount of energy that is required to maintain vital physiological functions in an awake, resting, fasting and thermoneutral state. But there are certain conditions, that is the patient has to be awake, right? Resting. In a state of resting, that means the person should be at physical and mental rest. Patient should be fasting, that means the patient should not have consumed anything since 12 hours. And thermoneutral state, that means the patient should not be in extremes of temperature, either hot or cold. So what are the functions that are supported by basal metabolic rate? That means the vital physiological functions that we were talking about. That includes cardiac activity, pulmonary ventilation, CNS activity, renal function and thermoregulation. Now there is another term that is called resting metabolic rate. What is it? Resting metabolic rate is measured under non-fasting conditions and the subject is awake but not necessarily at complete rest, right? So resting metabolic rate is approximately 3% higher than the basal metabolic rate. RMR, that is resting metabolic rate, is more practical for clinical use, while BMR is more specific for research purposes. So basically, what's the difference? That in basal metabolic rate, one has to be in a state of fasting. That means 12-hour fasting is required for that. But in resting metabolic rate, it is not strictly required. In basal metabolic rate, it is the requirement the patient or the person has to be in a state of physical and mental rest, complete physical mental rest. Whereas in resting metabolic rate, the patient can be in partial rest, like it can be awake, person can be awake or restful. Measurement time. BMR is usually measured in early morning, whereas for RMR, any quiet time can be chosen. Basal metabolic rate is more precise when it comes to the terms of accuracy, whereas RMR is clinically practical. BMR value is lower as compared to RMR because RMR is 3 to 10% higher as compared to the BMR. Methods of measuring BMR. We have direct or indirect calorimetry. Indirect calorimetry, the heat production is measured directly in a calorimeter chamber. It is rarely used clinically, whereas in indirect calorimetry, the oxygen consumption is measured and CO2 production is also measured. So basically it combines the measurement of oxygen consumption and CO2 production. It is based on the principle that energy expenditure is proportional to the oxygen consumed. So what is the measurement procedure? We use apparatus that is called Atwater Benedict Roth apparatus. It is a closed circuit method using a metal cylinder that is filled with oxygen. In this, the subject breathes via mouthpiece for 6 minutes. CO2 absorbed using soda line. Volume of oxygen consumed, that is by liters, is measured. Right? The conditions that are required is that the patient should be awake but at rest. The patient should be emotionally and physically calm. The subject should be in a thermoneutral environment, approximately 25 degrees Celsius, and the subject should be in 12 hours of fasting. So this is a formula that can be used for calculation of BMR. Heat produced in 6 minutes is 4.8 into Y kilocalories. Y is the amount of oxygen that is consumed, right? So heat produced in 24 hours is 4.8 into Y into 10 into 24, which is equal to 1152 Y kilocalories. 4.8 kilocalories is the calorific value of oxygen utilized. Now there is another method, that is advanced measurement, which is using double labeled water, and this method uses deuterium isotope and oxygen 18 isotope labeled water. Now deuterium is lost via water only and O18 is lost via both water and CO2. The difference in the elimination rate reflects the CO2 production. This is known as Nathan-Levson method. It is used in long-term energy studies using growth, pregnancy, lactation and clinical disorders. So now we will talk about what are the factors which affect the basal metabolic rate. First is age. BMR is highest in infancy and early childhood, peaking around 5 years of age. Right? It gradually declines with age, especially in elderly, due to decreased lean body mass and metabolic activity. Second is sex. Males have higher BMR as compared to females. This is due to greater muscle mass and lower body fat in males. Next is environmental temperature. Cold climate, it increases basal metabolic rate as a thermogenic adaptation to maintain core body temperature. Examples: Eskimos, they show significantly higher BMR due to prolonged cold exposure. Then as physical activity and starvation. Exercise acutely increases basal metabolic rate via elevated cardiac output and muscle metabolism. Chronic starvation or undernutrition lowers metabolic rate as a protective metabolic adaptation to conserve energy. Fever. Basal metabolic rate increases by 12% for every 1 degree rise in the body temperature. This is due to the increased metabolic rate of immune and repair processes during pyrexia. Thyroid hormones. Thyroid hormones, especially T3, they are key regulators of cellular metabolism. Hyperthyroidism increases basal metabolic rate and hypothyroidism decreases the basal metabolic rate. They act by increasing mitochondrial activity, protein turnover and heat production. This is a summary table which basically describing various factors which modulate BMR. Age, sex, cold temperature, exercise, starvation, and thyroid hormones. Moving towards units and expressions, BMR is influenced by body surface area. Hence, it is expressed as BMR is equal to kilocalories per hour per meter square of body surface area. Right, but for in routine cases, it is difficult to measure the body surface area right away. So, alternatively, for clinical use, we use this equation: BMR is equal to kilocalories per kg body weight per day. So there is a formula that is called Du Bois formula, which was given in 1915 to calculate body surface area, which is given by this formula, where A stands for surface area in centimeter square, W is weight in kg, H is height in centimeter, and normograms are also used for practical estimation of body surface area from height and weight. So normal BMR values in adult males is 34 to 37 kilocalories per meter square per hour, and in adult females it is 30 to 35 kilocalories per meter square per hour. Now, simplified estimation for convenience, average basal metabolic rate is approximately given as 24 kilocalories per kg per body weight per day, right? This value is useful for quick clinical calculations and energy requirement estimations. Now there is another term that is called specific dynamic action. What is it? SDA, that is also called thermogenic effect of food or diet-induced thermogenesis, is increase in metabolic rate and heat production after ingestion of food. We might have experience, we all have experience that after we consume food, we feel warmth, we feel as if the heat is being dissipated. The reason for that is the metabolic rate increases and heat is produced after ingestion for digestion, absorption, active transport and metabolic transformation of nutrients. This basically STA reflects the energy expenditure that is required for all these activities, right? So STA includes energy used for conversion of simple absorbed molecules like glucose, amino acids into storage forms like glycogen, triacylglycerol and proteins. This energy is not newly produced but mobilized from body reserves, reducing net energy availability from the food. So for example, energy adjustment due to specific dynamic action. So let's say we have consumed 250 grams of carbohydrates. So theoretically the amount of energy that we are going to receive by 250 grams of carbohydrate is 250 into 4, since the amount of energy that we get from carbohydrate is 4 kilocalories per gram. So we'll get 1000 kilocalories theoretically. But now what is the cost of specific dynamic action? Right? It is approximately 10%. That means 10% of the total energy. So 10% of total energy, that is 1000, will be equivalent to 100 kilocalories. So the net available energy will be 1000 minus SDA cost, which is equivalent to 900 kilocalories. So SDA acts similar to activation energy in chemical reactions. So there are energy additions for physical activity. For example, if the activity level is sedentary, then about 30% of the BMR has to be added to the total energy requirement. If the activity level is moderate and heavy, then about 40% or 50% of the BMR is to be added into the energy requirement respectively, right? Additional energy requirement, if a lady is pregnant, then about 300 kilocalories per day, this much amount has to be added in addition to the daily requirements. And if it's in lactation, then about 500 kilocalories has to be added. These are added on the top of the basic energy needs to support fetal growth and milk production. So let's take an example. So there is 55 kg male who does a moderate work. So the basal metabolic rate will be, we have to use this formula, right? 24 kilocalories per kg body weight per day. So that will be equivalent to 24 into body weight, that is 55 kgs, which will be equivalent to 1320 kilocalories per day. In addition to it, the person is indulged in moderate work, right? So about 40% of the BMR has to be added. 40% of the total energy is 528 kilocalories. So total requirement is 1320 plus 528, which is equivalent to 1848 kilocalories per day, right? Now out of this we have to add specific dynamic action, right? And rounding, the final need will be 2100 to 2200 kilocalories per day, right? So this is the requirement of that person. This table shows energy expenditure by activity. So these are the various activities, and this is the amount of calories that are consumed per hour above basal metabolic rate. Thank you.